Hello, everyone. I'd like to present our work, couple more theory for arbitrary classical spin system. My name is Khristina Albitskaya. I was done it with my colleagues, Fedor Shuklin, Alexander Chernov, Mikhail Petrov in Russian Quantum Center and MIPT University. Motivation is that in optics, when you have some spectrum frequency from aspect ratio of some 3D resonator, you can observe mode coupling, and it is well studied, and there is a couple more theory in optics for that situation. So we decided to investigate and to find something the same in Magnonics. But the problem is that analytical solutions for the Landau-Lifshitz equations exist only in endless films, in thin films, or thin layer structures, in infinite rod of rectangular and cylindrical cross-section. But in the geometry that interests to us, simplest finite three-dimensional geometries like cylinder or sphere, there is separated, only separated and little done there in this area in analytical solution of the Landau-Lifshitz equation, and there is no couple mode description of mode interaction. We've done it. Let's start from theoretical overview. It's Landau-Lifshitz equation for the dynamic magnetization vector that is red. It's spin mode, Magnonic mode, it's synonyms. And we solve it for spin mode eigenfrequency, that's blue one. Here's M0 is a stationary magnetization vector. H exchange external field, H exchange field, L the exchange field characterized by exchange lengths, and the last here is a dipole demagnetization field. Each field we consider as a sum of stationary part and dynamic part. Then we can divide all modes into three types of spin modes. The first one is exchange mode, when this is 0. The second one, dipole exchange modes, is a total Landau-Lifshitz equation with all fields. And the dipole modes, when dynamic exchange field, this one is 0. So we have three type of mode. Geometry that we have investigated is a cylinder and sphere magnetized by external field along z-axis. And in the cylinder aspect ratio, diameter to the height of the cylinder is 1 in all my forward calculation will be. Material of our spheres and cylinders was bismuth, iron, garnet. That is popular in our quantum center. All dipole exchange modes, full equation. We have classificate in the cylinder by orbital momentum number in solution that proportional to the exponent in IM phi, and to the z-odd and z-even modes along z-axis, because the cylinder has a symmetry along z-axis. So all modes we can divide by these numbers. For example, like this one, M0 and even along z-axis, or this one, M the same 0, but it's odd mode, as you can see here. In all these graphs, amplitude is the color shows the amplitude, and red vector is direction of the Magnon mode. Okay, we have classified it. Let's look at the spectrum of dipole exchange mode. That all spectrum was calculated in COMSOL multiphysics. Here's a frequency versus volume of our cylinder. So here we can see some interesting things like this one. For it's a hybridization of the modes with M1, like this branch and this branch, and all even modes. We can see these interactions in the spectrum, and the same for the M2 and the same even modes. Here, hybridization area. Okay, let's see what we see and understand it more clearly. Mode interaction, what is it? It's when you have a frequency from doesn't matter which system parameter or some system parameter, and you see two branches, and along one branch one mode becomes another mode, and there is here like a hybridization area in these points. You can separate mode 1 from mode 2, and all this couple mode characterized by interaction constant G. Um, if we understand the whole theory, we can switch on or switch off the interaction between these two modes, and we will see spectrum with coupling like these two modes. And when we switch off this interaction, we will see only crossing. This is anti-crossing and this is crossing. So we decided to do the couple mode theory for investigate this J constant. What characterize it for Landau-Lift equation? That was the question. Okay, our Landau-Lift equation that we know from it's a five equation. The fifth equation, we construct the theory of the interaction of spin modes. This red one, yes, because here's a frequency of the red one modes, total equation, dipole exchange, based on the exchange modes that will be green. Okay, if we rewrite Landau-Lift equation for the exchange mode in the type 6, we can add the dipole operator to our equation, and equation 7 is the same as equation 5. It's one equation, but in different style. Okay, let's expand the dipole exchange mode according to the exchange basis. Red one from as a sum of the green one. Red one dipole exchange as a sum of exchange mode. And then let's introduce the integral of the dipole interaction of exchange modes with number n and k. Two exchange modes n and k interact between each other by this dipole operator. So we have this q and k. That's interaction constant. And using orthogonally of the exchange basis, we obtain an equation for the frequencies of the dipole exchange modes, the red one, yeah, total equation. In this matrix, and the interesting thing and the result is that we have obtained the interaction force G that we was interested in. We know what it depends on, because vanishing of the off diagonal terms like Q and K and Q K of diagonal terms, if we put it 0, that makes our dipole modes not interact and K. And we can switch on or switch off interaction doing some calculation with this matrix. So the last slide is here. Okay, let's look to this P. It's eigenfrequency, and this is volume of the resonator. Here we have two branches, and this circles is numerical calculation, income sol. This dash line is CMT not coupled, couple mode theory not coupled, like this one is when we vanish when we put zero non-diagonal terms, and we see this crossing, and when we this is black lines is a couple mode theory interacted is omega total matrix. Okay, and here we see a good matching with the numerical results. So our results for the first time, semi-analytical couple mode theory has been constructed for arbitrary three-dimensional geometries in Magnonics. Why I say arbitrary three-dimensional geometries? Because in all my calculations, I didn't use the cylinder geometry. So it's for arbitrary three-dimensional geometries. Thank you for your attention. I will be happy to answer your questions.
Thank you for the nice talk. Is anyone have questions? Okay, I have one brief question.
Yeah.
So can this model apply to other systems such as ferromagnetic or antiferromagnetic systems?
We have calculated everything for ferromagnetic system, yttrium, iron, garnet, but I think if we can consider anisotropy, we can apply it to the ferromagnetic system.
Thank you for the answer. And there is a question from the audience.
Yeah, I have one question. Yeah, please go ahead.
Me? Thank you.
Yeah.
Sorry. Yeah, thank you for the talk, Christina. Just a question. Did you compare your model with the experimental results? Or is it difficult to do?
Yeah, thank you for the question. Yes, in our lab, it's usual geometry like this iron garnet cylinder, and we have experiments with this, but my results is a spectrum from the volume of the cylinder, so it's a little bit hard to do many different volumes of the cylinder. So now we didn't have experiment, but maybe in the future.
Okay. Thank you. I'm pretty straightforward. Thank you.
Thanks.
Yes. Hi, Christina. Thank you for the nice talk. Can you go to slide 9? This next
9?
one. Yeah, just the next. So in the hybridization area that you say over here in this region of same hemisphere, pink region, do you always get these kind of coupled modes, or the hybridization area doesn't necessarily be giving a coupled mode region always? There is any other condition also there?
Yes, maybe I didn't understand the question well, but hybridization area characterize two coupling mode. When we
So
see
would that be
anti-crossing,
necessarily always be giving that anti-crossing region, or it is not necessary that always the hybridization area will give these kind of coupled modes?
as I know, in all specters where you see anti-crossing, it's characterize two coupled mode. Maybe I'm not right, but as I know in optics and as I see in Magnonics.
Yeah. Okay. Thank you.
It's almost time, so
Thank you.
yeah, let's thank the speaker again. Thank you for the presentation.